Swayam Prabha. Digital India. Educated India.
Welcome back. In Module 9, we will cover trip assignment, and in Lecture 41, we introduce it is Introduction to Trip Assignment. So, we will start with the background, and then we will look into transportation supply, the traffic flow theory, the network flow model, and then within network flow model, we will look into how to describe a network and to build a graph model. So, looking at the four-stage transportation model that we have been discussing in our earlier lectures, traffic assignment is the last step of the four-step transportation forecasting process. And in this particular step, trip interchanges between the zones are assigned to specific transportation routes, and as a result of that, vehicular flows are generated, and when vehicular flows are eventually loaded onto the transportation network. So, basically we have got trip interchange volumes, then we have got transportation routes, and then finally vehicular flows which should be loaded to a particular transportation network. Now, this means that whenever a person wants to go from zone I to zone J, then he will try to first find which route he should adopt. Now, route basically could be the shortest route, or it may not be the shortest route, or it could be the shortest cost, or it could be shortest length, it could be shortest cost, or it could be a combination of both. So, there could be different ways a person choose a route, and sometimes even a person when he chooses a route, and he needs to be also aware of that existence of that particular route. So, that is another issue that plays a role. And then finally, once the route is chosen, this particular interchange volume would be assigned to the route, and a route is composed of many many segments in the road. So, that actually results in vehicular flows in each of these road segments, which are added up, and these flows like one segment could be in multiple shortest routes or shortest paths between two zones, and in that way one segment gets loaded from different directions, and these vehicular flows are loaded onto the transportation network, and that needs to be ascertained. So, if I start with demand for travel, which is Qij, and K is the mode, that means I know from which zone, origin zone to which destination zone a person is traveling, and we also know his mode, then we need to load the total amount of vehicles, not individuals, vehicles into the network, and that actually is that is the supply side, that is the demand side. Whereas, from the transportation network's point of view, that means there is a certain network capacity, and if you are talking about transit, then there is also a capacity in the transit system. For example, capacity of transit depends on the transit frequency. That means the number of buses in a bus route network, a number of buses coming within an hour actually determines the capacity of number of passengers that could be transferred along that particular route. So, that means both transit frequency and network capacity, these are the two components which actually determines the total amount of transportation supply. So, there is always a sort of feedback in between this demand and supply, and at one point of time equilibrium is established. That means the total amount of origin and the total amount of supply matches, and what it means is whenever there could be multiple routes, that means that a person will choose not a single route, he may choose between many routes, and he will choose in such a way. There are different ways he could be assigned to the network, but ultimately equilibrium prevails. That means at the end of the day, if there are two routes going from A to B, we may find that in both the routes the load is the travel the interzonal volume is loaded in such a way so that the travel time is more or less same. So it may happen, it may not happen, but that is what is equilibrium. So we have got three components. One is demand for travel, the second part is route choice, and that has to be mode wise, and finally is link assignment. That means once we know the route along which a person is going to travel, or the vehicle in which the person will be loaded is going to be traveling, then we need to assign it to a particular link segment. So that because a route is composed of many links. So when we look into this trip assignment process, first, daily trips are divided per hourly, and it could be also divided based on peak and off peak hours. So that means even though we estimate TI QIJ values for in the interzonal travel volume for the overall day, but at the end of the day we have to determine a distribution to ascertain which hourly load, or or at least even if we don't do it hourly, we need to do it in the peak hour, off peak hour, and so on. And in that way we can determine that during off peak hour maybe 40% of the total load is concentrated within maybe 4 hours or 5 hours, whereas morning 2.5 hours, evening 2.5 hours, whereas the rest 60% is spread out all throughout the day. So in that way we can also decide. So direction of travel along a transportation network is also important, because in which direction the vehicle is moving, that is important. It's not only because our road segment has got always two directions, so that also has to be considered. And finally, as we are discussing, we are not talking about person trips anymore. So QIJ volumes are not has to be converted into vehicle trips. No, so that depends on mode choice as well as car occupancy. That means, of course, if a person goes by transit, we definitely know from which stop he is going to which stop, and we will assign that person to that particular transit node, and then based on the transit capacity, we will determine that if he would be able to go along that particular route or not, or if he is using a two-wheeler or a car, then we will decide, is he going to go alone or is he going to go together with some other people. So accordingly, we will decide on the number of cars that would be resulting from the number of person trips. So we are more concerned with vehicle trips, not person trips. So the data required to carry on this assignment process is we need to know the proposed or existing network, transportation network and facilities such as the links, the nodes, the transit network, the transit routes. All this data has to be there. And we only consider the major links, because if we look into the very small local street or even collector street, what happens is that means there is huge amount of data and the options would be suddenly it will be increasing exponentially or maybe even more. For example, if I am choosing road between 2 points, if I not try to also think about the smaller collector streets or even the local streets in between two zones, then we will end up with many route choices, and all of them would be near to the shortest path. So there is a chance that people have to be assigned to all this route equally. But actually when people do choose a route, they don't choose the local paths in the middle segment of the route. That means they start from a particular zone. They at the initial part of the journey they may use some local streets, and after that they get into a major corridor, major arterial maybe, and or a sub arterial, and then they carry on to their destination, and then again they will get into the smaller streets and all. In between they don't start looking into the smaller. Suddenly they don't go out and look into the smaller street. Well, I'm saying that is the assumption that we do, but sometimes when people have detailed knowledge about this network, sometimes people, to avoid certain congestions and all, they do get into some local streets and all, but in general it is not the case. So we are only concerned with the major network links, and we can overlook the smaller local streets and collector road. and it also depends on the disaggregation level and the size of the traffic analysis zone. So all these things play a role in the detail of the network that we are going to consider for trip assignment. So travel impedance, then we have to, once we do that, then we have to also understand what is the travel impedance at different times of the day along all the links that we consider, and this impedance has to be also considered as per the different modes. So that means there is impedance could be either travel time or travel cost, or could be a combination of all this, but let us assume for the time being it is travel time. So we need to understand the travel time for each mode, for each of the link that is there in the network that is under our consideration, or that has to be there. And what do we mean by travel impedance? We need to understand what is free flow impedance, what is link capacity, what are the intersection delays, along with the total travel time. So our travel time is actually composed of many parts. It is composed of the intersection delay, it is a result of the link capacity and the free flow impedance. That means if there is no congestion, then there is free flow, and that will take a certain amount of time, which is impedance, and then when the capacity increases, that will reduce. So all this information is required for this particular network. Then we have metrics of hourly or peak hour interzonal trips mode wise, so that we already discussed. So that data also we require, that has to be loaded onto the network. So to talk about the goals of traffic assignment, we need to determine the total interzonal trip impedance cost as feedback to trip generation, mode choice and distribution model. So if you remember from our earlier lectures, when we did trip distribution, we required the trip impedance between two different zones, and this is the step from which you get a feedback of the trip impedance, which goes into as input into the into the trip distribution model. And similarly, not only trip distribution, the amount of travel time also plays a role in determining accessibility, and accordingly it may affect trip generation, or it would also affect the mode choice model. So if you remember from mode choice model, when we did multinomial logic choice model, we discussed that we don't use what people say is the cost that they have experienced. We take the data from the network time schemes, and this network time schemes are generated from this trip assignment stage. So in that sense, this is the final stage as well as the most important stage in this four-stage transportation planning process. So all major once we know that total zonal trip impedance, and then the next thing is all major route choice, mode wise, transit network wise, for all for each interzonal OD pair, that also has to be understood. That means for each I origin to J destination, there could be some route choices, that is there are certain ways people goes, and this could also vary mode wise. It could also vary, of course, transit network wise, it will be as per the transit routes that are there in the city. So, but mode wise means when you are using a car, you may choose certain routes as alternative. When you are using a motorbike, you may choose certain other routes as alternative. So, mode wise also the routes that you will choose will also vary. But you can also understand this, that if you choose too many alternatives, then again the entire computational process becomes it would be too time consuming. So we also limit the total number of options for route choice. Maybe we will look into 2 or 3 or maybe maximum 4 routes. So if we go beyond that, then you can understand the amount of computation increases increases. You have to multiply that with that for each mode and all, and then that choices explode exponentially. So finally, traffic volume on each major network link and turning movement at intersections, these are also required. That means once we know the route choices, we will assign our traffic volume on each of these major network links, and when we do that, we will also get the turning movement at intersections. That means at each intersection, how many will go straight, how many will turn left, how many will turn right, and based on that, we will also determine the signal times. And when we know signal times and the arriving number of vehicles, we can also estimate congestion at each signal. And when we can estimate congestion at each signal, you can understand when the flow increases, the traffic signal pattern changes and the congestion and the queue length increases. So, if we can consider that, then automatically we will be changing the impedance of that particular link, and that means the link dynamically, the impedance in the link dynamically changes, and immediately sometimes people also do change their decision to choose a particular route. So, this part is called dynamic traffic assignment, which will be also covered later on, but that means that at certain intervals people update their route choices as well. So, in that sense, we need to have a detailed understanding of this traffic signals and all, just to also ascertain that what would be the total impedance and increase of impedance when the capacity increases, and that also influences assignment part as well. Even if we don't change the route assignment, the route choice, it will change the assignment, link assignment part as well. So, when we look at transportation supply, we can talk about two parts of it, and one is we estimate the flows resulting from users' demand on one hand and determine the technical and physical aspects of transportation supply and infrastructure on another hand. So, traffic flow theory actually looks into the first part, where traffic flow where we analyze and simulate the performance of the main supply elements. That means when there is more demand, how the system performs, and then also this actually takes into account the transportation supply or the physical characteristics of the transportation as well. And then there is the structure of the transportation network, which is looked into in the network flow models, where we look into the topological and functional structure of the system and how it impacts route choices, total impedances, and so on. So, two things that we need to consider: with increase in traffic flow, speed actually reduces. So, this is something fundamental which we will consider, and shortest path before trip assignment will change after trip assignment. So, that means it is not a single step process, we may have to determine assignment iteratively. So, that because when I am loading a particular link with traffic volume, then automatically the impedance will change, and this happens dynamically constantly. So, that means we have to do iterations. So, at one point you will see there is no change, and that is the traffic volume, that is the link assignment that we will consider. So, when we talk about traffic flow theory, the models in traffic flow theory simulate the interactions among the vehicles which are using a given transportation facility or service, and this could be classified into two groups. One is called model for running links and the other is model for queuing links. Now, queuing links is mostly related with transit. You can understand that this model simulate the interactions among users waiting for us but receiving a service at a specific location. For example, number of users in queue, vehicle arrival time, headway between arrival time, service time of vehicles, waiting time. So, as you can understand, there is a certain number of people waiting, and there is a headway in between two buses maybe, and that determines how many number would be waiting in queue, and then based on the arrival time we can also understand how many people will be cleared. So, that actually also, and how many people will not be cleared. So, from that we can also determine the waiting time of each passenger, and so all these things are estimated when we are doing models for queuing links. And using this kind of work, we can actually determine the load on our transit network and what kind of transit capacity has to be provided and so on. And or rather how many people would be going through transit, that also could be influenced from this. And the other is of course the model for running links, that we will be primarily concerned because we can always assume that the transport authorities or the transit authorities will design their transit as per the demand that comes to it. So, even though that is not the case always, but a transit authority should design their service as per the number of people arriving at each particular bus stop or a railway as well. So, accordingly the service has to be provided. Whereas, for road network, this process is a little bit more dynamic. That means this in the model for running links, this model simulate the interaction among users moving along the same transportation facility, and here we considered the length of the road segment, vehicle speed, headway between different vehicles, number of vehicles crossing a point at a given point of time, and then spacing between vehicles. All these things are considered. So that actually basically points towards what is flow in a particular corridor, what is the concentration in a particular corridor, and what is the total speed in that or travel time in that particular corridor. And speed or travel time is basically the impedance that we are talking about. So that means based on different loading pattern in a corridor, this impedance will also change, and this actually plays a role in traffic assignment. So, in this particular figure, you can see the relationship between three primary components of this fundamental equation, which is speed flow concentration equation, where Q is equal to UK, where U is mean speed, K is concentration or density, and Q is flow. So, these three things vary simultaneously. So, as you can see in this particular graphs, so we have over here and we have plotted Q by Km. Here it is U by Km. U is speed, Km is concentration, and Q is flow. So, we can see that UK relationship is monotonically decreasing. That means this is U, UF is free flow speed. That means there is zero, when there is zero concentration, then speed is maximum, it is free flow speed. Then more concentration increases, the speed comes down at one point of time. So that means it's a monotonically decreasing function. Q and QK and QU relationships are backward bending. That means they increase and then they are decreasing. So that means Q and K gradually, when K is concentration, when concentration is increasing, that means Q is increasing, Q is flow. That means total vehicles passing per hour, that is flow. So that means more is the, because speed is also increasing, speed is decreasing and concentration is increasing, that means flow is increasing, but at one point of time it will start decreasing again. And same happens over here. Speed actually is you can see that, okay, at this part is Q max. So at this is the point beyond which we cannot, speed doesn't decrease further. So this is the maximum point, and you can see this UM is maximum flow Q max. This is where the maximum flow happens. It happens at this point which is at speed of UM, and this Km is concentration. Km is also have reached the highest point. So maximum flow Q max happen at intermediate speed UM and concentration Km, and UF is free flow speed. So we can see that the traffic flow is inversely proportional to speed. The reduction rate of speed decreases as the flow reaches the link capacity, and in traffic assignment generally the speed flow relationship is handled in terms of travel time per unit distance versus flow, and this we call a cost flow relationship. That means instead of speed we take the travel time for a particular unit distance in terms of travel time per unit distance, and so instead of speed versus flow we take this travel time versus flow, and we because travel time is a form of cost, we call it cost flow relationship. So this is fundamental equation that we will use in assignment. So here you can see the cost flow relationship. We can say that with increase in flow towards capacity, average stream speed will decrease from free flow speed of UF to speed at maximum flow UM, and thus also increasing the impedance. So that means impedance also increases gradually, and this relation between link flow and link impedance is called the link cost function. Now in this particular equation you can see that over here we have got Q max, this is this particular point, and in this equation, and then at one point you can see this will become flat. So that means it will not increase further, and over here in this particular equation we can see that this W is basically the time. So over in the general equation given by BPR, Bureau of Public Roads, link impedance travel time at different flow vehicles, the flow is vehicles per hour of a link is given using this particular formula, where T is equal to congested link travel time, T0 is the original link travel time which is free flow time, and then this V is the assigned traffic volume and C is the link capacity. So, V by C. So, we have always heard about V by C ratio. So, this is volume by capacity ratio, and that means it based on the volume by capacity ratio there is actually reduction. So, V by volume by capacity is always capacity is when it is less, then we will actually when volume is more, then automatically this gets added to 1, and increases the travel time from T0 to T. So, V by C is not directly used. So, we use this calibration coefficients, which is alpha and beta. So, these are model parameters, and typical values which are used is alpha equal to 0.15 and beta is equal to 0.40. So, so over here this we see that in this particular equation at 1.15 W we are getting this then beta value becomes 4. So, over here, since the minimum path changes with trip assignment, so this alpha and beta values are assumed to be 1.5 and beta equal to 4, and these are the calibration coefficient, and V by C could be for that particular when V equal to C, for example, this becomes 1, right. So, in that sense 1 to the power 4 is also 1. So, this is 0.15 and that gives us 1.15. So, 1.15 T0 becomes T. So, over here you can see 1.15 W dash. So, this is what we have considered, and then so that means this is when we have reached the volume has reached capacity, we are reaching 1.15 W. So, that is how we are arriving at this, and we can see at this point this is the speed this is the travel time at maximum flow. So, maximum flow is basically the maximum when capacity is achieved. So, since the minimum path changes with trip assignment, the number of iterations are performed till convergence, and this could be called capacity restraint methods. So, we will discuss that in later lectures. So, now coming to the network flow model, we need to describe the network in a certain way. So, we have already talked about links and nodes. A link is a segment between two intersections in a network. A node can be either be described as a zone centroid or the intersection point of two segments within a network. Now, it could be intersections between two segments definitely, but zone centroid actually refers to whenever we are having a TAZ, we are assigning that particular trips originating from the TAZ into a particular link. So, for that we need to take a point from where the trip originates and then we have to link it to the network. So, usually the zone centroid is the point from where the traffic volume from that particular TAZ is loaded into the network, and it is usually not loaded into a intersection or into a connection between two links. It is usually linked to a middle of a particular link. So, in analysis of road network, what we do is, so this is the links, and this is how we define the links and nodes, and then what we do is the road network is abstracted as a coded network. We use the term coded network, and what that means? That means that each of these links and the nodes will be given certain attributes, certain values, and this forms the matrix for those particular node, and this could be we can process using computers, and because manually it is very difficult to have a large network, to process a large network. So, we do some calculations, we use matrix calculations sometimes, which actually could be processed in computers faster, and that is why we also do not include this local and minor streets to reduce that overall complexity of the network. So, different link characteristics like link travel time, distance, level of service, capacity, facilities and geometry are coded, and then these are also coded into the network that we actually design. So, links are chosen in such a way that physical and functional characteristics can be assumed to be homogeneous for the whole link. example the same average speed. So, if you find a corridor with maybe there may be multiple intersections, but if you feel that that particular stretch is more or less same and there is not too many connections from other centroid zones in between, so we can make it into one single link as well, which will include some signals, but in most cases we will do it from signal to signal or from one intersection to one intersection. And nodes can correspond to points with different space and or time coordinates in which events occur. So, that we can understand. That means it has got different coordinates, that means different locations, and also at different times their attributes may also change. And the direct entry or exit times in a road segment, an intersection, a station may be associated to a single node representing all the entry and exit events. So, this could be done either entry could be at entry or exit could be at a road segment or at intersection or at a particular station, which could be a transit station as well. And centroid nodes represent the beginning and or end of individual trips, and I said already that we can load it to a middle of a road segment, which is the most cases we do that, but in cases we can also load it into a station or we can load it into a particular intersection. Path K is then comes the concept of path. Path K is a sequence of consecutive links connecting an initial node, which is the origin node, and a final node, which is the destination. So, a path is a combination of multiple links and it connects the origin and destination. And only paths connecting centroid nodes are considered in transportation graphs. Why? Because origins and destinations are centroid nodes. That is why we will only consider the paths between the centroid nodes. All other paths between intermediate intersections or nodes are not considered. So, this is the image of a city. This is the network for a city. C is the city. We have got different zones A, B, C, D, E, F, and so on. And each zone is connected to another through routes. And you can see these are all directed routes. And we have also used dotted lines for bidirectional routes. That means flow is in both directions. And when we use an arrow, that means flow is only in single direction. So, this is another way we can look into this, and the other things we have already described. The first thing is we need to consider interzonal vehicle trips and not person trips, and accordingly we need to develop the matrices, and then we need to also consider the diurnal distribution of trips. We are not going to consider the overall 24-hour day period. How many trips to go from one zone to another. It has to be for the distribution has to be hourly or for peak hour, and then we are also we also need to know the direction of travel of trips to be assigned to a transportation network. So, this is also very, very important. So, this is how we can look into the data. We can organize the data. We have origin zone A. These are the destination zones B, D, E, F, I, J. And we need to first segregate as per work, edu, and others. So, these are the different trip purposes, and once we have the trip purposes, then we have to load it into the as per the different time of the day, that is 6 to 9, 9 to 11, 11 to 14, and so on. We will load that trip purpose onto this, and as per the time segment we will load that into the matrix, and once we do that, the next step is to determine how many of these people will use which mode. So, after that we can also do mode wise also another level of categorization. So, we have walk trip wise, and then we have time wise categorization, and similar matrix needs to be prepared for other zones. So, this is only for zone A, and row wise addition will give us number of daily trips for each trip purpose. As you can understand, all walk trips for the entire day. This matrix consists of person trips which needs to be translated to vehicle trips prior to assignment. So, once we know the mode choice, we will convert those trips to the particular mode, and that actually will help us to decide on what would be the total number of vehicles that would be loaded onto the particular route segment. So, this is how we actually code the network. So, if I have a map, there are different roads within it, and we can have different zones. So, actually we do it like this. So, zone 1, this is a centroid zone, zone 2, these are centroid zones, and from here we are connected to 6. So, centroid zone is loaded in the intermediately to a link. So, the link volume is 5 in this direction, and from 1 to 6 it is in this direction. Then from 6 to 7 this is the total link volume 8, and from these are the impedances, sorry, to 8, and then from 7 to 6 it is 7, and so this is how we will code the entire network. So, this is the root network diagram that we prepare, and these are the impedances for each of this route in each direction. So, when we do graph models, network could be represented in graphs, and the coded network could be represented through these graph models. And a graph is an ordered pair of sets represented by G equal to this NL, where N is the set of elements known as nodes or vertices, and L is a set of links or arcs, where L is a subset of N into N. So, this N into N number of total links are present, and this is a set of pair of nodes belonging to N. So, this is how we represent the entire network. So, we can see G, this is the entire graph. G is equivalent to N and L, and N we have got 1, 2, 3, 4, and these are the nodes, and L link there is 1, 2, 1, 3, 2, 3, these are the different links, and that is what is being shown over here. So, once we have that, then we can also create something called a link path incidence matrix, and what it means is it's a binary matrix where delta can represent the relationship between links and paths, and that means which link belongs to which path, and we use this delta actually to determine if a link is within a path. We use delta equal to 1, if it is not, then it is delta equal to 0. So, in that way we can say that which links are included in which path. So, if it has a number of rows, so in this particular link path incidence matrix, we see that the total number of rows equals the total number of links NL, and the number of columns equal the total number of paths. That means on each column we will list the paths, on each row we will list the different links, and then we use 1 or 0 to represent if that link is within that path or not. So, that is what is stated here. Row of link path incidence matrix corresponding to generic link L identifies all the paths including that link, columns k for which delta Lk equal to 1. Same procedure is adopted for columns as well, that is row L for which delta Lk is equal to 1. So, over here you can see the link path incidence matrix. So, this side we have got the paths, this is from OD pair. For 1 to 4 there are 3 paths. So, it starts like in this 1, 2, 3, 4, or it could be from 1 to 1, then 2 and 4, and it could be in this way 1, 3 and 4, and so on. So, these are the 3 ways. From 2 to 4 we can go like 2, 3, 4 like this one, or from 2 to 4 directly, and then 5 to 6 could be gone using 2 ways only. 2 to in this particular 5 and 6, 2 to 4 is this, and 3 to 4 we can only go in one particular way. So, these are the different for 1 to 4 there are 3 paths, for 2 to 4 there are 2 paths, and for 3 to 4 there is only a single path. And in this side we have got the links 1, 2, 3, 4, 5, there are 5 links, and we can just put in this first path there is link 1 is present, link 2 is not there, link 3 is present, and then link 4 is not there, and link 5 is present. So, that is how we represent the entire link path incidence. So, that is one actually shows the incidence of that particular link in that particular path. So, once we do that, then we need to determine the cost of each path, and because that is what we eventually we want to determine, that is which path is the shortest path, and that depends on the least cost path between between each origin and destination pair, and each path k is associated with a path cost, and which can have 2 different attributes. One is the non-additive path cost, and the other is one is the additive path cost, and other is the non-additive path cost. Additive path cost depends on link flows. That means when the link is more congested, the cost actually increases. So this cost varies spatio-temporally. That means in each link and in different time periods, we will see the cost will vary. So that means when flow increases, the cost of that particular link increases. And there are also other costs, that this cost us, which are non-additive path costs. This cost a specific constant for each link, which is specific to a path or a OD pair. So this is a fixed cost that you have to give. That means if there is a bus fare along a particular route, that is fixed, whereas the travel time, it will vary. So if I have a generalized cost function where we have got cost of the fare plus the travel time, then automatically one will vary as per the congestion levels, other will remain fixed. So this is given by this particular formula, where G is the vector of total path cost for a network, delta T is the inverse of the link path incidence matrix, C represents the link cost vector, which is this additive path cost, and GNA is the vector of non-additive path cost. And so delta T is basically the inverse or the transpose of the incidence matrix. Now let us see how it looks like. So in this example, this is the same example that we used earlier for the network. We take the link incidence matrix discussed previously, and let us assume that the cost of the links are as follows. Link 1 is equal to 2 units, link 2 is equal to 1 unit, link 3 is equal to 3 units, link 4 2 units, and link 5 1 unit. And what will be, so we now, and we also say that the total GNA is also in the 0. So we see that GNA values are 0. So this is the link, this is the incidence matrix delta, and inverse of that incidence matrix is given by delta T, and you can see we have now taken the inverse of this particular matrix. So 1 0 1 0 1 has become 1 0 1 0 1, and so on, and this is the inverse matrix, and then this is the cost 2 1 3 2 1 are the cost of this different links. This is the cost, and GNA is all 0, considering non-additive cost to be null. So then we multiply inverse of delta, this transpose matrix along with C. So this is matrix multiplication. So we multiply 1 into 2 plus 1 into 1 plus there is nothing else. So in that way, when we do that, so we actually can multiply with this this particular way, and then we and then we arrive at the path cost, which comes to around G is equal to 6 4 2 4 2 1 for each of these particular paths. So path 1 is 6 units, path 2 is 4 units, path 3 is 2 units, and path 4 units, and so on. So that is how we are multiplying this with this, because it is matrix multiplication. We follow matrix multiplication rules, and we arrive at this path cost. So these are some of the references you can use. So we can conclude by saying that traffic assignment is conducted to derive and estimate different patterns of vehicle movements along the transportation network. Then aggregate estimates of the network, such as total vehicular flows, total distance covered by the vehicle, total system travel time, etc., can be computed using the trip assignment models. Travel costs between different zones can be estimated which helps in estimating or refining other steps of the 4-step travel demand forecasting model. And finally, trip assignment can also help in determining supply side deficiencies or the impact of provision of transportation infrastructure and amenities. So when we load a trip to a network, if it exceeds capacity, we may also determine to provide that excess capacity. Thank you.